Uh, Hello, am I audible? Okay, I'll assume I'm audible. So welcome to the week 8 live session of the course NPTEL NOC25 EE-39. The course is titled Fundamentals of Semiconductor Devices and is taught by instructor Professor Vijay Nath from IISc Bangalore. I'll be the TA for this session. And the schedule for my sessions is every Sunday 3 p.m. to 5 p.m. Let's quickly go over through the guidelines. In case you have any query, you can ask it in the chat window, or you may raise your hand if you want. Please ensure that your microphones remain muted, especially when you don't intend to speak. And I would appreciate your cooperation to make this session an interactive one. Please keep pen and paper handy along with a scientific calculator, which I'm sure you would have already. The recording link for this session and the lecture notes will be shared by the NPTEL course team in the due course of the time on the NPTEL course website. Now, prerequisites for this session include the lectures that we taught last week, right? And it covered the following topics. You were introduced to MOSFET, right? And you read about gradual channel approximation, and then IV characteristics were derived. Then you saw substrate bias effect and subthreshold conduction in MOSFET. And then you saw some short channel effects in MOSFET, right? Is there anything that needs to be discussed as a recap? No? Okay, I'll assume doubts are cleared. I mean, don't have any doubts. So let me start this session with following. Before moving on to the problems, I wanted to discuss following thing. Is your gate, is your drain, and this is your source, right? What determines that this is drain and this is source? Okay, before that, is MOSFET a symmetrical device or a symmetrical device? Am I audible?
Yes, sir.
Okay, so please answer it. So is a MOSFET a symmetrical device? I mean, you can compare it with this, right? What about this? You also read about diode, right? PN diode. Is PN diode a symmetrical device or asymmetrical? What about
Symmetrical.
this? I mean, symmetrical or not symmetrical? I mean, symmetrical is going.
Symmetrical, sir.
This one is symmetrical?
Yes, sir.
Okay, please explain in what sense?
Sir, actually, sir, in case of PN device,
Mhm.
Sir, I think it is asymmetrical because the work
Asymmetrical,
function
right?
level are different, sir. Asymmetrical.
Yeah, the
Yes, sir.
thing is, when you interchange the polarity, right? I mean, suppose I am applying a bias A to the P node, and I'm applying some bias B to the N node, right? When you interchange these two biases, suppose this is some voltage and this is some voltage. When you interchange the biases, if the characteristics they remain same, then that is a symmetrical device, right? I mean, in layman's definition. And if the characteristics
Resistance is the example of symmetrical device.
resistor, yes, the resistor is an example of a symmetrical device. I mean, because even if you interchange the polarity, it hardly makes any difference to the circuit operation, right? The characteristics remain the same. IV characteristics remain the same. Now, what about MOSFET? Now, I'm concerned
It is
with
also
symmetric. It is
it is a I think symmetrical device, sir.
symmetrical. Okay. Which two terminals should I consider for symmetry in MOSFET?
Drain to source, sir.
Drain and source, right? Okay. So why is that the case? Why is MOSFET symmetrical? Okay. What determines this terminal is drain first?
Sir, hello, sir. In case of source, we can uh, inject electron, and in case of drain, we can take the output of electron.
No. Let's keep it simple. I'm saying, suppose I gave you a device. See, you said that this particular device is asymmetrical, right? Meaning, if I interchange the terminals, that would completely change the operation of this device, right?
Yes.
And
In
in
case
this
of sir,
case, let's write a resistor, right? Say I had A and B in resistor. If I interchanged these two terminals, the characteristics of the resistor will not change, right? They would be invariant if we interchange these terminals, right? So in that sense, you said that this is symmetrical device. Okay. So what I'll do is, instead of writing drain and source, why don't I write it as A and B? Okay. Is this
yes,
device
sir.
now symmetrical?
Yes, sir, symmetrical.
It is
Due to
symmetrical,
gate,
right? Due to what?
to gate,
Absence of sir, gate.
No, absence of gate. See, we already said we'll talk in terms of these two terminals, right?
Sir, it is symmetrical, sir. Symmetrical.
Now, if this is symmetrical, then how come will I decide which terminal is drain? Suppose I gave you some polarity, right? Suppose this is some VA voltage, this is some VB voltage, and someone will ask you which terminal is drain and which terminal is source. How would you answer it?
Which the terminal is positive, sir. This is with source.
Both are positive. How will you handle that case? I'm saying
Sir,
VA is positive and VB is also positive. Now, which terminal is drain and which terminal is source?
which is higher potential, sir.
Okay, VB is higher potential.
Then, sir, VB will be source or VA will be drain.
No, I mean, you were going on the right track, but I mean, you were right in the sense that you asked about the relative uh, magnitudes of VA and VB, but the
Yes,
higher
sir.
potential terminal would be the drain terminal, right?
Yes, sir.
Right. So if VB is at higher potential, then this B terminal would be drain. Is this clear?
Yes, sir.
Okay. So now let's see what I guess I should. Yes. Now let me do one thing. Now let this be drain, this be gate, and this be source, right? Now, what will happen if I connect drain and source? Sorry, drain and gate. Is there anything special about this? I mean, normally our MOSFET, in our MOSFET, your drain and gate terminals are not connected, right? What if I short them?
So it will be form a diode, sir.
It will form a diode. Good. And if you talk in terms of MOSFET, this is actually called as diode connected MOSFET. And what about uh, region of operation of this MOSFET? In which region of operation will this MOSFET be? It turns out it would be in one of the regions of the operation.
Sir, repeat the question, sir.
Okay, the question is, this diode connected MOSFET lies in which region of operation?
The transistor, sir.
What?
Gate voltage, sir.
No, I mean, see what I'm trying. What determines if your MOSFET is in saturation or not?
Sir, it is in reverse bias, sir, I think.
No. It's not about reverse bias. The thing is, I'm interested in knowing the region of operation, whether it lies in linear region, whether it lies in saturation, whether it lies in subthreshold or what. That is the question precisely. So before answering this question, I'm asking another question. What determines if the MOSFET lies in saturation region? You would have read this, right? In course content.
Sir, still
Is
now
there
it
any?
is not it.
No, you would have read, I'm sure. I mean, if MOSFET would have been taught, if
No, sir. Sir will told, sir. We are not personally me or not visit all the
okay,
lectures.
you haven't. Okay, got it. You haven't covered all the lectures. So there is a condition imposed on VDS, right? Drain to source voltage. What is that? It has to be greater or equal to some particular
VGS, sir.
voltage.
VGS.
It's actually VGS minus VT. Okay,
VGS minus VT.
VGS minus VT, which is also known as VDSAT, right? This particular voltage is known as VDSAT. So if this condition is satisfied, then the MOSFET is in saturation region. So now, since you know this, can you comment on the region of operation of this? So if VDS is less than this VGS minus VT, then your MOSFET would be in linear region, right? Now, what about this? Here, your VDS would be equal to VGS, right? So
sir,
what can we conclude from that?
So, sir, it is not in saturation region, sir.
Your VDS is equal to your VGS, right? If your VDS is equal to VGS, how will you compare?
Sir, it is in linear region, sir. Linear region.
It is in linear, sure.
Yes, sir. Because above equation, what you are right, VDS greater than or equal to VGS minus VT. So
Fine.
there will be equal to.
And I'm just saying that your
right
VDS is equal to VGS.
Okay. Sir, sorry. This equation fails, sir.
No, but still, it would lie either in linear or saturation. I want one amongst you to answer it. I mean, it's just maths, right? If VDS is equal to VGS, what can you comment on this?
Sir, this is the condition for linear region, na? Operation in linear region.
This is the condition for saturation. If your VDS is beyond this VGS minus VT, your MOSFET would enter in the saturation region, right?
Okay, sir. Okay, sir.
Now, what about this?
So,
if now listen, if VDS, yes.
If VDS equal to, sir, VDS equal to VGS, then it is in linear region, sir, I think.
Okay, you think that it's in linear region. What about others? Sanjeev Garji, would you like to answer this?
Yes, linear, sir.
Okay, you also are with the linear one. Anyone else who thinks it's in linear? Okay, does anyone think that this would lie in saturation region?
No, sir.
No? Okay, let's see.
No.
If VDS is equal to VGS, can I say that my VDS would be greater than a quantity that is less than your VGS? Does this make sense?
Sir, absolutely.
I mean, talk in terms of numbers, right? 2 was equal to 2. I can say now
Okay,
that
sir.
2 is greater than 2 minus 0.1,
No,
right?
sir, it is in saturation. Sorry, sir. Sorry, sir.
Right, this would be in saturation. Correct.
Yes, yes. Sir. Sorry, sir.
No issue. So this would be in saturation. So to summarize, what we saw is if drain and gate are shorted in a MOSFET, that is called a diode connected MOSFET. And the special about such kind of a MOSFET is that this always lies in saturation region. Is this clear?
Yes, sir.
Okay. Right. This is your diode connected MOSFET. Okay, what else can I discuss about this? Okay, what about this substrate bias effect? Right, how does that impact? Let's draw a MOSFET, a rough sketch, okay? This is the N plus and N plus source and drain. As I mentioned that what will determine if it can first take a contact before us. Suppose this is contact A, this is contact B, and then you have gate. This is your gate, right? Okay, what will determine which is drain and which is source? Okay. I mean, if I don't apply bias, can you comment on which terminal is drain and which terminal is source if I don't apply bias to A and B?
Sir, your voice is breaking, sir.
Voice is breaking. Uh, am I audible?
Now it is okay, sir. Now it is okay.
Okay, now it's okay. Okay, so what I'm saying is, suppose I don't apply any bias, right? Can you comment which say I did not apply bias?
Sir, if you don't apply any bias, sir, what what we want to comment, sir?
Can you come which terminal?
Drain or source, sir. Drain or source. Sir, it is interchangeable, sir, I think.
It is interchangeable. So A can be drained, A can be source. B can be drained, C can be source. The only thing that would make it drain or make it source is applied back. So this is something that should be clear. Applied bias in such a way.
Sometimes your sir voice will break, sir.
So why second breaking? Am I audible now?
Yes, sir, you are audible, sir.
Am I audible?
Now it is audible, sir. Audible.
Okay, can you speak again?
Sir, you are audible, sir.
Confirm.
Sir, is my voice is breaking, sir?
No. I mean, your voice is fine.
So, sir, I think if your side some internet issues there. I think.
No. Now it should not be there. I mean, now I kept the input as the mic of my laptop, so I don't think now there will be any issue.
Okay, sir.
Which terminal is this?
Substrate, sir. Substrate.
Substrate, or you can say body, right? Whatever.
Body.
Content. Right. So the question is, there is case one when your substrate, your source and body is shorted, right? So your VBS is 0, right? You'll have
Yes, sir.
you will have some threshold voltage corresponding to that, right? And then there is a case when they are not short. And
somebody's mic is on, sir.
Whose mic is on? I mean, the thing is, since I switched on the mic of my laptop, so I mean, I won't be having noise cancellation, right? Either you'll have to bear with.
Okay, sir, no issue. Okay, carry on, sir. Sorry, sir. Sir, there is a threshold voltage is there, na?
The second window corresponding to this is a DC valve. It's nice. This is these voltages. It's each. And then there is these two. When we are doing this, it's load of these two. It is these two. Right? When you comment on the relation with the this is.
So your audio is not clear, sir.
Is it clear now?
Yes, sir.
Yes.
Now it
Now
is
audible,
clear.
sir.
Okay. I'll repeat your question. Please bear the noise if there is any, because if I'll switch on the mic of my laptop, then the neighboring noise can interfere. So we have two cases, right? The case one is without substrate bias, right? And in that case, your VBS is equal to 0. Suppose the threshold voltage corresponding to this case is VT1. And then there is case 2, when you have substrate bias into the picture. In this case, your VBS is greater than 0. Suppose the threshold voltage corresponding to this case is VT2. Can you comment on the relative values of VT1 and VT2? Which one should be greater? And why?
Sir, in case
Firstly,
2, VT2 is
yes,
less
VT2
than
is what?
1.
Are you telling this? VT2 is less than VT1. This? I mean, is this what you are saying? VT2 is less than VT1?
VT2 is greater than VT1.
Yes, right. This?
Yes, sir.
Okay. This is correct, but I need the reasoning. Why is this so? Why is VT2 greater than VT1? So in other words, you are saying when you are uh, applying some positive voltage to the body, or in other words, have some substrate bias, the threshold voltage is greater in that case compared to the case when no substrate bias is applied. Why is this so? I'm saying this is correct.
Uh,
I'm
uh,
asking reason. Why is it so?
V, VPS greater than 0, some positive integer.
Okay,
And
when VBS is greater than zero, you have some positive field in this direction, correct? Then what will that field do?
P type, sir.
And I think channel will be created much less voltage.
I mean, channel will be created at a much less voltage for which case? Case 1 or case 2?
Case two, sir.
Case 2. So in other words, you are saying this is not the case, right? You are saying VT2 is less than VT1. Is that
No,
what you're
sir.
saying?
You already told that VT1. This is correct, sir.
But as per your sentence, you said the channel will be created at a lesser voltage for this case. If channel will be created at a lesser voltage for this case, then the threshold voltage will be less, right? Because what determines the emergent channel has formed, that is your threshold voltage, right?
Yes, sir.
So somehow we need to come up with a reason as to why the channel is formed at a higher voltage in this case compared to the voltage in this case. This threshold voltage is what? This is your gate to source voltage, right? VG, isn't it?
Yes, sir. Yes, sir.
And when you apply positive gate voltage, what will be the direction of the field? This it, right?
Downwards, sir. Downwards.
Right, downwards. So we have two fields. One is this. We write this as VG due to gate drive. And then I have another one. EV, both are vectors. So this is this is okay. What is EB? This is field, right? I'm applying some body potential. So now the question is, I mean, are these fields competing or are these fields assisting each other? They are competing, right? They are in opposite direction,
Yes, sir.
right? Now,
Yeah.
suppose I was having inversion channel at a particular gate to source voltage, which was corresponding to particular EG, right? Okay, what is net electric field? This is EG, this is EB. What is net electric field?
Sir, EG difference EV.
Uh, EG minus EB, right? And
Yes.
um, yeah, now the case, okay, threshold voltage would be corresponding to some gate to source voltage, right? That would be corresponding to some gate voltage, right? And that gate voltage would correspond to some E net. right?
Yes, sir.
Let's suppose that E net is your E naught, right? E naught is what? At E naught, your inversion channel is formed. So I'll say that this would correspond to VT. Is the idea clear roughly what I'm trying to point out?
The last sentence one more time, sir.
Okay,
E
I'll
net
repeat
equal
it
to
again.
EG minus EV.
So the
E net equal
inversion
to
channel
equal.
will be formed at a particular gate voltage, right? At a particular field, because
Yes, sir.
we have competing fields, right? So let's talk in terms of the CNet, right? So your inversion channel will be formed for a particular value of E net. And I'm saying let that E net be E naught. Okay, at E naught, I'll have inversion and that would mark my threshold voltage, right?
Okay.
Now I have two cases. In case one, I don't have this EV, right? This one. If I don't apply any body potential, then I won't have this. At that, in case one, for my case one, E naught will be equal to EG, isn't it?
Yes, sir.
Now case two. What happens in case two is I'm applying EB. So my E net would be less than EG.
Minus EV.
Right? It would be less than EG, right? There would be some value that is subtracted. So E net would be a value that is less than EG. But so case two. Is E naught greater or less than EG? What is,
Less than, sir. Less than.
yeah. So my E naught is
Less than EV.
less than EG, right?
Yes, sir.
No, I mean, I guess we said the other way. This should be the case, right?
Yes, value will be reduced, sir. Okay, okay.
I was having inversion corresponding to some gate field. Right? Now, when I apply EV, do you guys agree that I'll have to apply more EG to compensate this loss? Right? I'll have to apply some delta EG again, which would be equal to this. Right? So that my E net is again E naught. Does this make sense? I'm talking about this case, like case two.
Sir, in first case, sir, you told that if the base terminal is 0, then E net equal to EG.
Yeah, in case one, my EG was sufficiently larger. Now it was equal to this E naught. Now,
Yes.
when now EG value won't change, right? EG will remain same. Now, when I apply EB, what will happen is E net would reduce. Will E net reduce?
Yes, yes, reduce, sir.
And E net will be less than the value
Less
of
than
E
EG.
naught.
Less than EG.
It would see it would be less than E naught.
Yes,
Right?
yes.
It would
Yes.
be less
And
than
E
E
not equal
naught.
to EG. E not equal to
Right?
EG.
E not equal to, okay, I guess this is
E net.
what about now? This was equal to. And in this case two,
Sir, E net is less than EG.
yeah. But we need E net to be equal to uh, EG. So in other words, we need to increase this net electric field. Now, how will we able to do that is by applying more gate to source voltage, right? VG. So in other words, our threshold voltage would increase. I hope this is making sense.
Yes, sir. Clear.
Okay. So in case 2, when substrate bias is present, my threshold voltage VD2 would be greater than for the case when the substrate bias is absent. This is a layman's explanation.
So, sir, if the substrate bias is absent, we require less amount of gate voltage to turn on the device.
Yes, and when we have positive this, right, positive voltage
We
to
have
this
to
poly terminal, then we need to
require
apply
more gate
more
voltage.
gate voltage to
Yes, sir.
compete with this speed, right? That is roughly the idea as to why the threshold voltage is created. And in this case, and you would also have seen the formula, right? Threshold voltage in presence of what substrate mass. Have you seen that?
Sir, I have.
VTH is equal to VTH not as gamma square root of VTH is to 5 minus square root of 5. Here this VTH naught is the threshold voltage in absence of substrate bias effect. And gamma is the body factor which we saw in the previous session as well. Right? But gamma is square root of 2 Q epsilon is NA whole divided by CX. Okay, so this formula which is good, and that is the reason why this gamma is known as body factor. Because in a way, the magnitude of the gamma would be an indicator of how strong the threshold voltage would depend upon the body mass. Okay, that's why it's called as the body factor. I mean, we saw gamma in the previous session, so we can watch the previous session. Check. Right. Okay, then I'll assume you know this. And then let's move on to the questions. I will be leaving some questions as assignment. And, and then what I'll do is we'll have around 1 day of time to try it out. And after 1 day, I'll send you a link with the solutions to these questions that will be marked as assignment. Is that clear?
Yes, sir. So you give this question as an assignment.
No, I mean, this would
Tuesday,
be, you'll not need to submit this assignment. This is just for your practice. So the questions that are marked as assignment, you will be suggested to try that at your own. No need to submit that. If you have any problems,
sir,
you can.
I think I just want to confirm that you are taking another class in Tuesday.
I won't be taking class. It would just be a recorded video with solutions of the discussions. I'll record the video. And, okay. So this would be assignment problem, right? We'll try this one. Question 2 as well. So today is Sunday, right? Tomorrow is Monday. Tomorrow evening, I'll post a comment on this recorded video. I mean, you'll see this video or this session in the recorded form as well. Tune into the comments. There would be a link, and when you will go to that link, you'll see the solutions of these questions in that link somewhere. Okay. The first two problems are assignment. I'll leave problem 3 as assignment as well. Reason being, I want to discuss more interesting problems in the remaining time. This is a problem that I would discuss live here. So this is question 4, right? First, I want you to try this out a couple of minutes. You can have a look at this. We are given two identical MOSFETs which are connected in the fashion as shown. Right? Which of the following statements are true regarding M1 and M2? Have these two MOSFETs in one MOSFET and in two MOSFET. Right? And you need to conclude or comment upon what is true regarding M1 and M2. Right? These are your four options. Option 1 is that both N1 and N2 operate in saturation region. And second option is that they both operate in linear region. Third option is that your M1 operates in linear and M2 operates in saturation. And the fourth one is that your M2 operates in linear and M1 operates in saturation. Okay, so how will you proceed? Your M1 and M2 are in series, right? So the currents would be same, right? The current flowing in M1 would be equal to the current flowing in M2. So what I can do is I'll be taking one by one these cases later. Let me take this A first. ID1 is equal to ID2. Why I can write this is because M1 and M2 are in series. And then they both are in saturation. So I'll write what? It would be some factor mu C ox WL by 2. I'm clubbing that as beta. So beta by 2 Vg is 1 minus Vt whole square. That is equal to beta by 2 Vg is 2 minus Vt whole square. This is equal to what is VGS1 with this? What is VG for M1?
For M1.
Hmm.
3,
Yeah,
3 volts.
it's 3. And what is source?
5
Vx.
source ground Vx.
No, it's not grounded, it's Vx. So your VGS1 will be 3 minus Vx. You agree?
Yes, sir.
And then I'm having this minus Vt also. That is equal to, I cancelled out this beta since both are identical. Scale that they are identical MOSFETs. Now, what about VGS2? What would VGS2 be equal to?
3 minus 0, sir. 3.
So 3 minus V2 whole square. Right? And the only way this equation would be satisfied is when Vx is equal to 0. And when your Vx is equal to 0, then your
Output saturation, sir.
when your VDS2 would be equal to 0. Okay? Because when this is 0, this is drain, this is source, VDS is 0. And what is the condition that we need for saturation? What do we need for saturation?
M2, sir.
The condition that we need for saturation, I already discussed it some bit. I radio. So for this M2, we can write VGS2 minus VT, that is VGS2 is greater than this VGS minus VT. Right, and this is violated, right? Why? Because VDS2 comes about as 0. Is violated. So this implies that M2 is not in saturation. Right? Because we did assume that the MOSFET 2 is in saturation. So that is a wrong assumption that we took. Now, similarly, so it can discard this. Similarly, what we'll do is we'll see if this makes sense for you. What will you do for this case? And again, you need to equate the currents, right? But what is the equation that you use? Or in other words, is there any way that I can discard option 2 by using the definition of saturation? Let's use the definition of saturation in M1. Right? If I use it on M1, then
The last option, sir.
option D, yes, that is the correct answer. So let me just now show why second is wrong, and then as one student already answered, last one is the correct option. So what about M1? For M1 to be in saturation, right? If M1 in saturation, then VDS1 is greater than VGS1 minus VT. What is VDS1? That is 5 minus Vx. That is greater than. What is VGS1? Yes. What is VGS1?
Three, sir, three.
Hmm?
Three.
3 minus Vx. And then minus VT. So, I mean, VT would be, let's assume that
Three
VT
minus
is less. Yeah. So, can I say that?
I greater than C minus VT.
Yeah. So the point that I'm trying to make is, will this condition hold good for realistic values of Vx? It would, right? Just 5
No,
minus
sir.
Vx. See, 5 minus Vx was already greater than 3 minus Vx. And then I'm again subtracting Vt from it. So that would further lower it down. So this quantity would be less than this. So in other words, this holds good. So what I can conclude from this is M1 is in saturation. Now, if I concluded that M1 is in saturation, then automatically option B and option C will be discarded. Because M1 is in saturation and option B and option C says otherwise. As per option B, M1 is in linear region and so is the case with option C. So the only option left is option D, which I leave as an exercise for you all to convince yourself. Okay. This is that. How will you proceed with option D? Is you liquidate the currents, but while liquidating the currents, you will take N1 in saturation and N2 in mean. Okay. I'll just write the equation. So for this, we will do this. N1 will be saturation, N2 will be mean. And N1 saturation will be beta by 4 3 means is VT whole square. So equal to beta P minus VT minus V square. This is clear?
Sir, what is not clear, sir? Some extra noise is coming, sir.
Okay, sorry for that. So let me repeat what I said. So now, in order to prove that option D is right, we'll equate the currents. But while equating the currents, we'll take M1 in saturation and we'll take M2 in mean. The M1 in saturation involve this and M2 in mean. And then we'll proceed and we'll convince that this equation does make sense for realistic values of leaks. That doesn't make sense. So we'll proceed. So now we have option, sorry, question 5. In the circuit below, your M1 and M2 are two identical MOSFETs. So the acceptable value of the node voltage peaks is 1. If this and the previous questions are correct, if this is exactly same as this. And the information that I gave you is option D is correct. So you take M2 in linear and M1 in saturation. M1 is saturation. So I leave of saturation, the question that I use is this. If you have any doubt, just let me know. And for linear, I use this. I choose this to this one. It's easy. Radius, which is radius, and it's radius square. So it's square. Radius here is this one, this, which is radius. This would be the 3 minus why? Because my GG is 1 is
3 minus VX.
That's what. What about this VG is 2?
That is 3, sir. Directly 3.
Okay, so I'll take this 2 here. That's why I'm writing 2. Beta and cancel. 3 minus 18. Right, now what we'll do is one way to solve this part. Solve this part. The correct way would be to use these values of Vx one by one and then see if the obtained value of Vt Okay, we have one equation. How many unknowns are there?
Two, sir, two.
Two. And what are those two unknowns?
Yes. What's that?
What are the two unknowns? Vx and
VT and
Vt.
VX.
Yeah. So what I'm telling you is the options that are provided are for acceptable values of Vx. So you have four options of Vx. You'll plug in there one by one, and corresponding to each value of Vx, you obtain. Once you put the value of Vx, suppose I fix this, right? I fix this. Fix this with some constant. Fix this with some constant. This equation will be having only one unknown, which is this. Vt. Got it?
Okay, sir. Okay.
Okay. So what I'll do is I'll put Vx equal to 0.41. Like it, I'll get Vt is 1. I mean, do this exercise and you come to the same answer. So the Vt value that you'll get corresponding to Vx equal to 0.41 is 1. Similarly, if you'll put Vx equal to 1.4, turns out the value of Vt that you'll get after solving this will be quadratic, right? So the quadratic equation in Vt when you plug in the value of Vx. So the Vt value in this will be conjugate pairs minus 0.2 plus minus 0.1. Okay. So this is not acceptable, right? The Vt cannot be imaginary. And it turns out these two are also not acceptable. Why are they not acceptable? It's left as an exercise for you to answer. So plug in the value of Vx as 1.81 there and here, and then see what Vt value you get. It turns out they are not acceptable.
These also give some complex numbers, sir.
I mean, not necessarily complex, but the values would not make sense. That would be absurd. Suppose we get Vt that is greater than 5 volt. That will also not make sense. Right? The Vt cannot be greater than 5 volt. So this is what we cut off. So
Okay,
this
okay.
is question 5. C and D similarly you find out. The correct option is this. Now what about
A,
6?
sir. Correct option.
Sorry?
Correct option is A.
Yeah, correct option is
Correct option is A.
yeah. Right. Now what about this? The circuit above your suppose your VD is doubled from 2 to 4 volt. Which circuit? The same circuit. The circuit has not changed. In this circuit, you double the value of the drain voltage from 2 to 4. Okay, sorry. Let's complete the circuitry. Sorry, for question 6, the circuit of interest is this. If you double the drain voltage from 2 to 4 volt, the ratio of the currents for respective reading is 1. Firstly, we already saw in the introduction such kind of a MOSFET. What is this MOSFET known as? We discussed it, right? Which two
Sir,
terminals are shorted?
diode-based MOSFET
Diode MOSFET. And what is special about diode MOSFET?
is in saturation region, sir, always.
It's in saturation, right? So I'll write following. A MOSFET is in saturation. Reason is your gate is connected to drain, and we saw why that is. So therefore, I'll directly write the ratio. The ratio of currents, right? ID1, ID2, roughly. The VGS1 minus VT, but VGS2 minus VT, whole square. This would be where VGS is equal to VDS. Do you agree? Do you agree?
Yes, sir. Yes, sir.
Yes,
Always,
sir.
always.
Yes,
I can
sir.
write this, right? For diode continuous. So my VGS1 will be same as VDS. And what is VDS1? That is 2.
2 and 4, sir. For VGS1, 2, VGS2 is 4.
Correct. This will be something like this. It turns out this is 1 over 3 square, which is 1 over 1. So the ratio is ID1, so ID2 is to 9. Is this clear now?
Yes, sir. Yes, sir.
Okay. Similarly, we have in this question. In the same question, if your VD is changed from 2 volt to 3 volt, the current increases 16 times. What is the value of the threshold voltage of satisfies? Between and right?
Sir, it is, sir.
Now, the question is already giving you the ratio of the current, so it's asking you to compute the value of the threshold voltage. Right? 2 means VT. Here, VT won't be 1 volt, right? In this, VT was 1 volt. We can reduce it to 1 volt. So, right? But this
Yes, sir.
4 means VT will be equal to 4 times 2 means VT, right? I took sorry. After the 3 times VT is equal to 4 and yes, it's equal to 4 and
1.3, sir. 1.3.
yeah. And then problem 8. Right? Let's keep this as a sign note as well.
Sir, 1 means last slide, sir.
Sorry?
Last slide, sir.
Okay, last. Yeah. So
Last slide, sir. Last slide. Previous, sir. Previous, sir. Previous one, sir. Previous one. 1:16, sir. 1:16.
yeah, please.
Okay, 1 minute, sir. 1 minute.
Sure.
Okay, sir.
Fine.
Okay. Okay, sir. Done, sir.
Question 8 and was on second and we get the we discuss this one. You will be following VTH is equal to VTH naught plus U naught. And I already showed you this equation. And it was 5 square root of 5. What is this equation? This is threshold voltage in presence of substrate bias. So the question is that for an N-channel silicon MOSFET with gate oxide thickness as 10 nanometer, the substrate sensitivity is found to be 50 millivolt per volt, and at a substrate voltage VB is equal to 2 volts, where VT is the threshold voltage of the MOSFET. Assume that VBS, the mod of VBS is greater than Q5B, where this Q5B is the separation between the Fermi energy level EF and the intrinsic level EI. Okay, we need to compute doping concentration of this. So we have been given the value of the substrate sensitivity. So what is this as an expression? Del V equal to LPS. Del V equals del V means that's equal to, I mean, if you take derivative of this with respect to people, this is a constant, right? So this won't come. This will come. See this the square root of various please mod of the five of 8. And if you assume that your this previous is much greater than the two square root of this than over 2 square root of various assuming what assuming that your various is greater than 5. Fifty millivolt per volt into 2 square root of 2 is your common. Right? Why I took the value of EBS as 2 is because this is right. So what is the expression of gamma? I showed you in the previous session. It's square root of 2q epsilon is all divided by C epsilon. Right. So this will be 0.1. So if you multiply 2 with this will be 100 millimeter 0.1 times square root of 2. That is equal to square root of 2 cube epsilon is CF. And this would be damage for minus 3. That is equal to I'm taking square on both sides. This will be Q. Also, this 2 and 2 will go. It will be Q epsilon is ME by CH plus. And epsilon of and D of should also be given. Is D of given?
Yes, sir. 10 nanometer, 10 nanometer.
Yeah. So we can write any is minus 2 times epsilon square. We just do this velocity. We plug in the numbers. 13 will be equal to 7.35 into 10 to the power 15 centimeter cube.
1 minute, sir. 1 minute.
Yeah.
So this video lecture will be uploaded, sir.
Yes, this will be uploaded, and also the solution to the problems that I left as an assignment that would come as a link in comments after one day. I'll leave one day for you all to try them first. That's fine.
Sir,
Yeah.
sir, can you explain, sir? After the
Yeah,
differentiation,
please.
you put the 50 millivolt per volt into 2 root 2 for the uh,
No, I took this
house. Sir.
there. I took this there, and I was
Okay,
left
okay,
with
okay,
only
okay.
gamma. Okay.
Gamma.
So the value of this I
Then
used
gamma
as
value will
this.
be put you.
Gamma have dependency
Okay.
of any. So the only unknown is any. Rest of the things all were known. That's why I was able to find any. Is this fine now? That is what I have.
Yes, sir. Yes, sir.
So this I'll
So
leave
1
as
minute,
an
sir. 1 minute.
assignment.
Last, last. Okay, sir.
Fine. So this I'll leave as an assignment. Now, what about this? To reduce the parasitic things like table data scale, what is the best way? Firstly, you need to recognize that this is due to short channel effect. And what happens in short channel effects is gate doesn't, gate is not able to exercise that much control, right? So if you surround the gate and hence increase the gate control, you you'll be able to reduce such effects, right? So that's why option A is correct. You cannot reduce the gate control because that has already reduced short channels. So this is also wrong, right? Parasitics would occur due to scaling. So we need to change the gate architecture. We cannot leave it as understand. Okay, is question 10 clear? So that would be the objective on short channel effects. And then you have last question for this issue. You need to select all the what statements which are true. What about first statement? The interface states they affect the subthreshold swing of the MOSFET with the presence of additional capacitances, which is true. The presence of the trap charge in the oxide shifts the CV characteristics curve of a MOS system to the left or
Explain, sir.
right. Sorry,
Sir, kindly explain, sir, this.
which one?
First one, sir. First one. Okay.
First one. Okay. Wait, actually. Was subthreshold swing introduced in the lectures that you saw?
Okay, sir, got it.
I can still explain if, see, your subthreshold swing is your KT by Q, and there is ln 10 factor as well, right? So it's 2.3 KT by Q n, where n is your slope factor, right? And this slope factor n has that dependency. Your slope factor n is 1 plus C day by Cx. So that is the reason the interface states would affect the subthreshold swing of a MOSFET in the presence of additional capacitances. Okay, it's this in from which the dependence of the capacitances come into the picture. Is this clear?
Yes, sir.
Okay. What about second? Is this correct or wrong?
True, sir.
True, right? Because the presence of the trap charge in the oxide would change the flat band voltage in the CV characteristics
Yes,
of the
sir.
MOS system. And once flat band is disturbed, this would be laterally shifted right or left based on the magnitude of, the nature of the change. What about C? C is wrong, right?
Wrong,
Because
sir. Yes.
we already said that this
Opposite of the second sentence.
correct. What about fourth one? Charge present in the oxide semiconductor interface has strong effects on the threshold voltage, which is
Yes.
also true,
Correct, sir. Correct. Correct.
right? Because yeah, what? Why does this affect? Because they would affect the field, right? I mean,
Yes, sir. Yes, sir.
that. So now the assignment for you is the problems that I left them as homework, and we'll also
Yes.
do some relevant problems from the book. Keep up. Please go ahead. Do you have any questions?
Sir, is this assignment question you will send to mail?
No, I won't be mailing it. I mean, you
So I can take
you
the
will have
screens.
access to the recording. No, you don't need to. You don't need to take the screenshots. You'll have access to the recordings, and you'll also have access to the lecture notes, right?
Yes. After one day. Tomorrow I can.
No, I'll give you access today only.
Okay.
I
No
mean,
issue.
I'll be uploading different videos after one day. That I won't be uploading. I would be including as a link in the comment of the video that I'll upload today. Okay, so
Okay, sir.
keep tuning to that video. You'll get to know.
Thank you, sir.
Thank you. That's all for today.
Thank you, sir.